So let's assume that we have an equilibrium point. How can we linearize around that equilibrium point in order to get an operating region for our system? So again, as in the previous example, we're using the simple model for predator-prey calculations that was developed by Lotka-Volterra. So x1 represents the prey population, x2 is the population of predators, and we're assuming that both of these values are greater than or equal to 0. So the system of equations is made up of two ordinary differential equations. They're not so ordinary actually, because we have some nonlinearities here. So that's what's making this hard. So we have x1 dot is ax1 minus b x1 x2, and x2 dot equals minus dx2 plus c x1 x2. So we're assuming that the constants a, b, c, and d are equal to 0. This is important because this is a constraint of the system as it was developed by Lotka and Volterra. So now I'm assuming that someone's given me 2 points about which they'd like to linearize the system, and that these 2 points are equilibrium points. So the first point is x1 and x2 equals to 0. The second point is x1 equals d over c and x2 equals a over b. So with this in mind, now we're going to take the system of equations and try to develop at the equilibrium point what the linearization would be for each equilibrium. So we take the partial derivative of x1 with respect to x1. And when we do that for this equation x1 dot, we get the partial derivative of ax1, which equals to a, minus the partial derivative of bx1 x2 with respect to x1. That's just minus bx2. So it's fairly straightforward to develop these derivatives. We can see that the partial of x1 dot with respect to x2 is minus bx1. So the minus bx1 x2 is the only place where x2 shows up. So the ax1 is treated as a constant. The partial of x2 with respect to x1 is fairly straightforward. This is just cx2. And the partial of x2 dot with respect to x2 is minus d plus cx1. So these four values are our equations for the partial derivatives with respect to x1 and x2 respectively. So now let's choose x1 of 0, x2 of 0, which equals to 0, 0. Let's choose this as our equilibrium point. And we're now going to linearize around this equilibrium point by evaluating these partial derivatives and creating a matrix A. So we evaluate a minus bx2 at 0, 0, minus bx1 at 0, 0, cx2 at 0, 0, and d plus cx1 at 0, 0. So once we perform this evaluation, we get a matrix that's diagonal a, 0, 0 minus d. So basically, our system of equations for delta x dot is equal to this matrix A times delta x. So this gives us our linear representation of this system at the equilibrium point. So again, for small disturbances around delta x, so for regions really close to the linearization point of 0, 0, this system will be valid. So again, this is the linearization at x1, 0, x2, 0 equals 0, 0. Alright, so let's look at exactly the same case, but now for a second equilibrium point. So this is exactly the same as before. I repeated it on this slide to make it a little bit easier to understand. So at the second region, x1 of 0, x2 of 0 is equal to d over c and a over b respectively. So earlier in a different example, we calculated that this was an equilibrium point of the system, basically where x dot was equal to 0. So now let's write in a straightforward way, let's write our matrix A, that's the state update matrix. So A minus B x2 evaluated at our operating point, minus B x1 evaluated at the operating point. The same for C x2, and minus D plus C x1. So if we evaluate this matrix at these points, we get 0 minus BD over C, after we substitute in x1 equals d over c, ca over b, and 0. So this is also a diagonal matrix, but it's diagonal on the other diagonal. So this is our gain matrix, this is our matrix A for the state update equation. So delta x dot is equal to this matrix A times delta x. So if we remember that delta x is actually x minus x0, and x0 is actually d over c for x1 and a over b for x2, now we can take this update equation and write it based on its initial conditions. So here I've replicated the gain matrix A and gone ahead and written now x minus dc over and a over c is the two vector values for x0. So if we rewrite x as the vector x1 and x2, now we can write this system of equations as one large matrix. So minus bd over c times x2 minus a over b times bd over c. So it's sort of hard to see this if you haven't done matrix algebra in a while. But basically, the 0 that we have is preventing the x1 values from showing up. So this 0 here means that we don't consider x1 and we don't consider d over c. We're only considering a over b, and we're multiplying a over b times minus bd over c. Or you can imagine it as just subtracting x2 minus a over b here, and then multiplying this by the gain in this matrix. So if you haven't done matrix math in a long time, you might have to do this on paper by yourself. Similarly, we get some multiplication by ca minus b. Since this is in the first column, we're going to multiply this by x1 minus d over c, which is what we see here. So now let's separate this out in terms of just x1 and x2. It may seem like we're just writing exactly the same equation, but we're not. Now we've separated out the multiplication of bd over c and ca over b, so that we can write it separately. So let's assume that we have some input u of t, which is a step input. So now we can actually write this system with a b matrix of dA over c and minus dA over b. So I want to treat this matrix like a b, and I'm multiplying it by 1 of t. So now we have a state update equation. X dot is ax plus bu. So this now gives us the ability at the linearization point, x0, as long as delta x is small, this is valid. If we make delta x really, really big, then we're going to see that the linearization of our system will not match. And so the actual model's behavior will be different from our approximation of it using this linearization scheme.